Okay, so welcome everyone, 23 participants. I think it's a record. So let me welcome Jonathan Braden here, a postdoc from the Toronto University, right?
Yeah, technically CITA, but good enough.
All right. So Jonathan is going to tell us about analog preheating with Bose-Einstein condensates. And well, Jonathan, the floor is yours. Thank you.
All right, thank you. So my title basically summarizes what I will talk about. And before I get going, I'm hoping this will be informal. So if you have any questions, you have a flame, something's unclear, please just like stop me and we can discuss it. Okay. So just a quick overview of what I'm going to talk about. So I know this is a pretty diverse group of people, and certainly not everyone is as used to thinking about inflationary cosmology as I am. And even fewer people are used to thinking very hard about preheating and how inflation ends. So I'm going to start with an overview of exactly what I mean by preheating and how that fits into our cosmological picture. Once that's done, I'll kind of review how we use dilute gas cold atom BECs to emulate relativistic scalar field dynamics and why that's related to cosmology. And then I'll get into how we can actually use these systems to do preheating or end of inflation. Okay. All right. So let's start with the cosmology part. So, over the last, I don't know, I guess let's say 50 years or so, we've come up with the standard model of cosmology, which is how we think the history of our universe has gone. And so we start with the Big Bang, 14 billion years ago on the left here, and we really have no idea what happened there. Okay, it's like some quantum gravity regime. People have ideas, but we have really wide open unknown what happens. And then sometime shortly after the Big Bang, an effectively classical universe emerges where there's like a constant energy density driving exponential expansion. And so the universe gets very, very big very quickly. And this is needed to basically seed the little fluctuations in the density that are everywhere in the universe that later will collapse to form galaxies and stars and clusters and all the structure that we see in the universe. Okay. Of course, we don't currently live in anything that looks like a very cold inflationary universe, so that had to end at some point. Okay, you make all the particles and you end up with a very, very hot bath of standard model particles. And this is what you would usually think of as the hot Big Bang. So the universe is very, very hot. There's tons of particles and they're in thermal equilibrium. The universe keeps expanding, things cool off. Many things could happen that we don't really know. You can have phase transitions. At some point, you have to make an asymmetry between matter and antimatter. You have to make dark matter in here somewhere. Okay, lots of very interesting theoretical questions. At some point, you get nucleosynthesis. And at this point, we sort of have an observational handle again on what was happening in the universe. You keep waiting. At the same time, the neutrinos freeze out. You get a neutrino background. Keep waiting, waiting, waiting. Temperature goes down, particles annihilate. Eventually, you're just left with basically hydrogen and electrons. And then at some point, the temperature drops enough that they recombine. The photons stop bouncing around between the protons and the electrons, and they just like travel in a straight line for the next 14 billion years. And we see them as the CMB. You keep going, structure starts to form. Eventually stars turn on, you make galaxies, you do all the things that we see in the universe around us, and then we get to here 14 billion years after the Big Bang happened, and we get to look back with telescopes and try and uncover what happened. And so this talk is going to really focus on this transition from inflation, which is necessary to set up kind of the initial conditions for standard cosmology, and to go into the case of a very hot thermal plasma. Which is sort of the older view of what the Big Bang looked like. Okay, and so a different way to think about this is really like starting the Big Bang, okay? And what's happening is our usual description of inflation is this very cold universe. There's no particles, there's effectively zero entropy, and there's only a few active degrees of freedom. We usually describe the dynamics at this time as sort of like, there's this field and it is the same everywhere in space to a good approximation. So like one number kind of describes everything. And you have to go from that to all the particles in the universe are there. They're at a very high temperature, above the temperature necessary to do Big Bang nucleosynthesis, so about 10 MeV. Huge amount of entropy, proportional to that temperature cubed in a prefactor. And there's a lot of active degrees of freedom, okay? And so this is a very, very, very violent event, okay? And so really what we're trying to do is understand the first part of making the recipe for the cosmic soup of standard model particles that existed in the very early universe. Okay, so that seems like a very ambitious goal to understand this. So like all good early universe theorists, I'm going to take the following viewpoint of the universe as there's some scalar fields and they interact with gravity. Okay. And so from that viewpoint, what we're really saying is, okay, I've got some fields and there's some potential. Okay, and during inflation, the potential is kind of flat. On scale sort of smaller than the curvature scale. The universe is more or less homogeneous. There's some like very small superhorizon perturbations there. And I can more or less describe this field, the fields as just like there's some mean values that are evolving in time. Then what will happen is at some point, you're kind of traveling along this potential like a ball. You presumably hit a point where you get around to a minimum of a potential and the thing will start oscillating around here, okay? And this is when inflation has ended. And now you need to understand how to transfer all this energy that's locked up in this inflaton field into particles. And so an important thing during this transition is that, during inflation, you're kind of saying subhorizon eigentrivia is homogeneous. After inflation, it becomes very important that the uncertainty principle does not allow you to set all the fluctuations to zero, okay? So there's sort of this mean field that's oscillating. And then on top of that are sitting these little inhomogeneities that are there because there's a commutator between phi and phi dot, okay? And if you start going about and doing microphysical modeling of what happens when you have a ball oscillating around the bottom of the potential, there's a ton of instabilities that you can get. And so the fact that these instabilities are there are really the essence of what people mean when they talk about reheating. Okay, so the theory for this was sort of worked out in the early to mid 90s originally by Brandenberger and Trashin, and then Kaufman, Linde, and Starobinski. And so the first stage of it, again, remember I said there's some homogeneous field that's oscillating, and then on top of it, there's little fluctuations. So you can do linear perturbation theory to understand what the dynamics of those fluctuations are. And very generically, if you ask what the Fourier modes are doing, they satisfy some linear equation of this form. And the key thing is that because the mean field phi bar is oscillating, V double prime of phi bar is also oscillating. So mode by mode in Fourier space, you have a simple harmonic oscillator with a time-dependent frequency. Okay, and if you've ever swung on a swing, which is basically a simple harmonic oscillator where you're allowing the center of mass and thus the frequency to change in time, you know that you can make the amplitude of your swing increase with time, okay? And so that is a very general statement about these types of equations, where if you have oscillators with oscillating frequencies, you will have exponential instabilities in them, okay? And so there's generally some band of wave numbers that grow exponentially fast in linear perturbation theory, okay? And so you're very interested in first of all, what are the wave numbers that are growing given a particular model and how fast are they growing? And so this plot on the right here is just showing for one specific field theory what these exponential growth rates look like. So everywhere that it's colored, you have an exponentially growing mode, okay? And the darker red the color, the faster the exponential growth is. Okay, So that's, of course, linear theory. If you want to do a full treatment, you need to include things like nonlinearity. So back reaction onto the background, rescattering between the different modes. Okay. And for that, you really do need to do lattice simulations. Okay. I just want to point out one thing with these. The way that preheating simulations are done is that we say, instead of solving a full quantum field theory problem coupled to gravity, we turn it into a statistical field theory problem. And so what you do is you say, I have my mean field that's going to be oscillating, and I grab a realization of the quantum fluctuations. I paste that in. And then from there, I hit go and solve classical equations of motion. Okay. But you pasted these fluctuations in and they couple to gravity. So the quantum mechanical part of the system is actually gravitating as well. So you do have some horrible combination of like non-equilibrium quantum field theory, quantum gravity. Okay. But this is an approximation, of course, but okay, it's what we can do at this point in time. Okay. And so what exactly does this thing look like? So what I'm doing here, sorry, yeah.
Question, sorry. What do you mean with, I'm puzzled. You said a couple to gravity. What exactly do you mean with this?
Okay, so the way it's usually done, you can be a bit more adventurous if you want, is you would say, I'm going to take an ansatz for the metric that is FRW. You then plug it into the action, and you get a self-consistent set of equations of motion where the scale factor in that metric is being driven by the dynamics of the field. So it's really, okay, this is not the way the equation solved, but this h squared is rho over 3mp squared. H squared is the curvature in the gravitational field. And this rho is like the mean energy density of the fields over the lattice. So the expansion rate of the universe is really being driven by all of the field content, including these fluctuations that you put in, that were supposed to be quantum mechanical. Does that answer your question?
Thank you.
Yeah. Yeah. You could be more adventurous than this, but here's the simple case. Okay. All right. So what I'm doing is this is a box that's sort of one curvature scale at the end of inflation. And what I'm plotting is the log of the energy density with time. And so initially the universe is nearly homogeneous. The energy density is more or less constant everywhere, but fields oscillating and modes are growing. And so as time goes on, you can see that and this is coming out of the quantum fluctuations, okay? And, as you can see, this is a very, very complicated looking situation that is, again, if you think about what's being done, we're saying there's a condensate, there's vacuum fluctuations on that condensate, and via dynamical evolution, those vacuum fluctuations are going to become huge order 1 density perturbations that subsequently drive all of the gravitational expansion, okay? So it's super wild if you think about what's actually going on. And we really want to understand what is going on here, okay? Now, a valid question at this point, which might be, why should I care? Okay, I'll give a few reasons for that, and then we will get on to the VCs, okay? So the first one is, okay, this is like non-equilibrium, nonlinear physics, which is really, really cool. Okay, so just as a theoretical exercise, this is a fundamental part of nature that's not particularly well understood, but allows for a lot of really interesting dynamics. And because you're also in cosmology, you have an intersection of sort of quantum field theory effects with gravitational physics. And so it's a bit of a window into quantum gravity. Okay, if theoretical physics is not your cup of tea for motivation, you also have cosmological motivation, which is our current theory of cosmology. We have inflation, which is necessary to make the CMB. And then you have sort of the hot thermal bath, which is necessary for BBN and to actually have standard thermal history in the universe. And you have to paste those two things together. And if you don't understand how to paste them together, you're basically saying, oh, there's this part of our cosmic history, I don't know, who knows, okay? That's a little bit unsatisfying to have a model that has a big strip taken out of it in the middle. Okay, if that motivation is not enough for you either, I think there's also good reasons observationally to try and think about how end of inflation works. And the reason I say that is that, all of our cosmological understanding at this point basically comes out of data from the CMB and from large scale structure. And so we have these wonderful maps of temperature fluctuations of where galaxies are located. These things have huge amounts of information in them. But as they relate to the early universe, it's effectively fixing two parameters. And it's two parameters describing a 2-point correlation function. Okay? Well, presumably we could use these data sets to do a little bit more than that, given that we have them. And especially the large scale temperature fluctuations, we're never going to get better data. So, people have, of course, looked for various things. One sort of prediction of inflation is that the fluctuations are very Gaussian. But, there's corrections to that. And so you might want to look for non-Gaussianity. The problem with that is saying, oh, something's non-Gaussian is like an almost empty statement. Okay, what do you mean by non-Gaussian? And if you want to go and look in your data, you don't want to just do a data mining exercise because you're going to find things. So you need some sort of like template that is motivated by theory that you can try and match onto your data. Okay. And because you're looking for non-Gaussianity, you want to look for epochs in the universe that are both nonlinear and non-equilibrium. And preheating dynamics is one of those things. And in fact, it's a very, very violent non-equilibrium event. So in some sense, it's a very good candidate for looking for things that are highly non-Gaussian. Okay. And so just a very quick example of the kind of thing that can happen. So if you run simulations, like big lattice sims, and then you ask, what do the density fluctuation dynamics look like? Really interesting forms of non-Gaussianity, where the zeta I think of as density fluctuations or fluctuations or fluctuations in gravitational potential. Okay, there's this Gaussian piece on top of it, which is a non-linear function of the Gaussian field. And so this is very, very different than the standard things that people normally look for. But if the typical way to look for non-Gaussianity is to do something like measure a 3-point function. This type of non-Gaussianity has a very small 3-point function. Okay. So it also has very interesting kind of spatially intermittent structure, where in some regions you get lots of action, lots of non-Gaussianity, and then in between that, there's not too much going on. Okay. And you can run different types of models. You'll find this is quite generic with preheating dynamics. And so, it's very interesting to say, okay, can we come up with some templates to look for these signatures of end of inflation dynamics and then actually go look in the data for this, okay? And that is making better use of the existing data and future data that we're gonna have, rather than just trying to, okay. So that's the end of the sales pitch, mostly. Okay. Having said that, as I mentioned before when describing the numerical simulations, all of this understanding is resting on some reasonable approximations and assumptions about how non-equilibrium quantum field theory works, but these have never been tested experimentally, okay? We don't know if our numerical and theoretical techniques are actually capturing all of the important behavior that happens in preheating, or if we're missing some super important effect that is just not captured by the approximation, okay? And so it would be really, really nice to have an experimental system that is a quantum field, behaves like a relativistic system, and does not require us to make approximations to put the quantum mechanics in, okay? And so that is, of course, where we get to analog systems. And I will specifically be talking about cold atom BECs here. And I don't really need to explain to anyone on this call why this is exciting, I don't think. But just, a quick review of the kind of things that people use analog systems for. I'm sure I'm missing many. But you can imagine trying to study things like Hawking radiation. So that's sort of a linear quantum mechanical effect, but it is fully quantum. You can also look for solitonic physics in these analog systems, and these are nonlinear structures, but they're really, really classical. And so then you could ask, what do the quantum fluctuations around like these really classical systems do? Another thing you can look at is first order phase transitions and bubble nucleation. So that is, of course, a very nonlinear phenomenon, and it's quantum mechanical. And what I'll be talking about instead is preheating, which is you start with quantum fluctuations that are linear. They grow, they become very large, and they start to interact with each other. And at this point, the system effectively becomes classical, but it's highly nonlinear. So it's kind of a combination of the linear quantum with the nonlinear classical and some transition between the two. Okay. So just a review for how we go about doing this and why you can do preheating with these systems. So the idea is to take two BECs, okay? And I will get to why we need two in a second. And you cool them down to some low temperature. In my perfect theorist world, they're at 0 temperature. Obviously not true in experiment, okay? And then you go grab yourself a laser of some sort and you couple them together in a very specific way, okay? And all right, you can ask, what is the way that we would model this experimental system? And the standard way of doing that is to say, okay, the BECs are some condensate of some bunch of atoms. And that is described by this complex field psi, okay? And that sort of has like a classically condensed piece and then some like quantum fluctuations around it, okay? And the equation of motion obeyed by this thing is something that's a nonlinear Schrodinger equation, more or less. So there's the standard thing that's just the kinetic energy, so p squared over 2m. There's a potential energy from this thing being trapped inside of some external trapping potential. And then the field theory part is sort of this psi squared term, which is capturing S-wave interactions in the for 2 to 2 scattering. And then the thing that is important to get preheating is that you have a coupling between the two that can directly convert one species of atom into another, okay? And this is just a linear coupling, okay? So on the surface, this looks like it has nothing to do with relativistic fields, and I want relativistic fields to try and connect to cosmology. So how exactly does that connection get made? So for now, I'm going to do a simplifying assumption and toss this trapping potential away, and I will get back to this later. And the reason to do this is so that, remember I said in cosmology, we start out by saying the universe is more or less homogeneous everywhere. So it's spatially homogeneous. If you have a trapping potential, then your background that you're expanding around is spatially inhomogeneous. So everything becomes much more technically complicated, even if conceptually we'll get the same behavior. Okay. So to pull out the relativistic fields, we basically just make a change of variables. So we rewrite the complex variable in terms of a square root of a prefactor and then a phase, okay? And this row here has the interpretation of a local particle density. Okay, the phase is a phase. In the relativistic field interpretation, it will turn out that these number densities are sort of like canonical momenta for the field, so phi dots, and the phi's basically will act like relativistic fields. Okay. Now, the assumptions I need to make, I'm going to make two at this point, is that the number density is some homogeneous piece. Okay. This is, I don't think critical, but it just makes all the math easier. And the important thing is that the fluctuations around this mean number density are small. Okay. So that really is critical to get a relativistic field description of. Okay. And a useful limit to be thinking about is that this nu is parameterizing the direct interspecies conversion rate. Relative to the chemical potential, it's very small. Okay, that's the limit we want to take. So your first hint that maybe you can get relativistic fields is if you just say, I'm going to do full linear perturbation theory in both the number densities and the phases. And you ask, what does the dispersion relationship look like for that? If you go to long wavelengths, so below the healing wave number, say, which is defined this way. So let's drop this k squared over k squared Field term. You get omega squared is m squared plus k squared, which is, of course, a relativistic dispersion relationship for a field. Okay, that's linear perturbation theory. We want to study nonlinear physics, so it's not quite what you want, but it's a hint that maybe something interesting could be done. I'm just going to skip this. So to really get out the full nonlinear effective field theory, it's useful, instead of looking at the number, density, and phases of the individual condensates, to look at the relative density and relative phase. Okay. And remember, I said the number densities were small, so I can integrate them out and get an effective Lagrangian for the relative phase. And when you do that, you will see that your effective Lagrangian looks like this. So it's a phi dot squared minus grad phi squared plus some function of phi, okay? And this is basically a relativistic field with a sign potential, sorry, a cosine potential. And for anyone who's familiar with these things, this is, of course, the Sine-Gordon model. So in 1D, this thing has lots of really interesting properties that I have zero time to get into. But it's integrable, you can do inverse scattering, you do all kinds of really fun math. For my purposes, the important thing is that this is a relativistic field with a potential that is periodic. And so if you can displace the phase away from zero initially and then let it go, it will start to oscillate around the minimum, okay? So remember, that was the way I was describing the starting phase of preheating, which is there's this homogeneous field oscillating around a minimum. And so, you can ask, okay, I did these mathematical tricks to tell you it was a Sine-Gordon model. Is that actually a good approximation? So in the top left corner, I'm just plotting a phase diagram showing how I've for the moment taken the field to be homogeneous. Okay, so I have a mean phase and a mean time derivative of the phase. Okay, the solid lines come from solving the coupled GPE. So the BEC dynamics. The dashed lines are solving an equivalent Sine-Gordon system, so relativistic field theory. And there's two types of motions. The black ones are where the field's oscillating around a minimum. The red motions are where it's like scanning over mini-minima. And as you can see from this, the Sine-Gordon approximation is a pretty good approximation, especially for the oscillating motions.
So, Jonathan.
Okay. Yes.
When you said before the density fluctuations are small, doesn't that mean these ellipses should be somehow squashed much more?
Ah, great. Okay, so yes, I should have mentioned this. So the density fluctuations are small, but this is phi dot, and so to go between the two, there's a square root of nu tilde connecting them. So phi dot is like density fluctuation over square root of nu tilde, and nu tilde is small. So you can have small density fluctuations in large phi dot.
Okay, fine.
Does that make sense?
Yeah, but still, what does it mean to say, like, I have integrated out the density fluctuation? Density fluctuation is still proportional to phi dot. And when you do like phi dynamics, there is a phi dot. It's not an equation just for phi. It's an equation for phi and phi dot. I mean, it's Lagrangian. So
Yes.
what's the density fluctuation is integrated out? I mean,
Okay,
they're
great.
proportional to phi dot.
Yeah. So this slide that I skipped. Okay, so what I specifically mean is I'm going to expand the Lagrangian up to quadratic order in the number density fluctuations. Okay. And when you do that, you'll get something that looks like this. Okay. So the green is kind of like the gradient energy and the potential piece are already in there. But there's a linear coupling between the density fluctuations and phi dot. Okay. And so then you integrate the Gaussian, okay? And if you have a linear term and you integrate it, you square the linear term. That's just how Gaussian integrations work. So you end up with a phi dot squared.
Okay, but isn't this delta rho already phi dot?
Let's see.
I mean, these are
I
the
see what you're
conjugate
asking.
variables, right? The density mismatch and the phi, right?
Let me think. This is a good question. I have not thought about exactly. I haven't thought about this in a while. Let's see. So this piece is coming from this piece is coming from the psi dot term in the Lagrangian. So the thing that gives you d psi dt, the equation of motion. Okay. I guess at some level, this is psi dot. Sorry, this is phi dot. So it's not delta rho. So the order of this term is a bit different than this term. Okay, I'll have to think about that a bit more and get back to you, Zora. Having said that, you know, you could just compare the two evolutions and they do match each other. Okay, so there's no integrating out in this top left panel.
Okay, but you agree, like when you set this up on the side of the potential, like you're like say the you know, on your top right plot, one of the arrows, right? I mean, one of the arrowheads, right? Then say at that point, you know, you have no phi dot, right? And then when you're at the bottom, the phi dot is maximum, and your delta rho is okay. And at the bottom, your phi dot is maximum, and your delta rho is maximum, right?
Yeah.
Okay.
Let me think.
I was
So for this,
like say you integrate to the previous slide. Sort of feel like they're really not integrated out.
so no. So I can give I can give you for this specific figure what that means. So this is just capturing the homogeneous dynamics. So that would mean you kind of integrated out all of the inhomogeneities. Okay, I'm not making an assumption that the background is small. I'm just making an assumption that the fluctuations are small.
Mm-hmm.
Okay, so for this particular figure, that will work out that way. Let's see. Okay, could I get back to you because I'll have to remind myself all of the technical details and what assumptions are being made when I do this. It's like a multiple page derivation that I don't have off the top of my head for you. Okay. But it is a valid question, and that's why I did check that, you know, I run the GPE side, I run the Stein-Gordon side, and they are matching. Okay, so it's not a crazy thing to be doing. Okay, is that good?
Yeah, sorry, I already muted myself.
Okay.
Go ahead.
Yeah, no problem. Okay. And you can do some more checks to make sure that everything really is more or less like Stein-Gordon. So you can ask, okay, I've got these periodic motions here. You can ask, what is the period as a function of the amplitude of the oscillation and this new tilde parameter? So here the color scheme is the period of the GPE over the corresponding period of the Stein-Gordon. And you can see at most there's like 20% deviations, even if you take nu tilde up to be like 0.2 or no, 0.5. Okay, so that's good. The period is more or less the same as you would expect. Okay. And so now the back, and what I've shown is that the background, you know, you can make undergo these periodic motions. So now you want to ask, suppose on top of that background, I put some fluctuations, and those fluctuations are inhomogeneous. Okay. And it's more convenient to work with sort of like the total phase, the relative phase, the total density, the relative density. And as I said before, so to go to like a canonical momentum here, there's a 1 over root nu tilde. Okay. So you think of these capital pi's as more or less phi dots. Okay. So that's why the densities can be small and phi dot can be large. Okay, so you get some horrible looking set of linear equations. Let's not worry about the details of these, short of they have the form dy dt is some linear operator times y, and that linear operator is periodic in time. Okay, that's all that matters. Okay, and anytime you have an equation that looks like this, you can grab theory from 100 years ago called Floquet theory that will tell you if this L is periodic, your solutions have the form y is some periodic function times e to the mu t, where mu is a complex number. And it depends on exactly what the form of this L is. And so if these mu's have a positive real part, you have an exponentially growing mode, okay? Which is like the key essential ingredient that goes into preheating, okay? You can also take the limit that nu tilde goes to 0 of this equation, and you will find the following effective equation for the relative phase, which I see has a typo in it, okay? Which is delta phi double dot plus k squared plus m squared cos phi delta phi equals 0. And this is the linear perturbation theory equation for the sine-Gordon model. And I already showed you that the mean field more or less follows the sine-Gordon evolution. So we have really reproduced the relativistic sine-Gordon model for the perturbations as well in linear perturbation theory. Okay. So of course you want to understand what do these instabilities look like. So you can go ahead and solve those. So here I'll just show for a couple choices of the amplitude what they look like. So on the top panel, this is the real part, the largest real part of a Floquet exponent is in red. I'm allowing nu tilde to vary. So as I take nu tilde to 0, I get the sine-Gordon equation. As I take it to be large, I really end up in more of a non-relativistic field theory regime. And then I've sliced along a few lines. And in the bottom, I'm showing this is what the growth rate looks like as a function of wave number k. And so the dashed line is the sine-Gordon. These colored lines are for various GPE solutions. And you can see, the qualitative form of these is like the same as the sine-Gordon for all cases. And as you take nu to 0, you do recover the sine-Gordon. Somewhat special thing here is there's one instability band and it extends all the way down to 0 wave number. That's not generic for all relativistic field theory equations, but it is true for the sine-Gordon. Okay, and you can take a larger amplitude, you get basically the same thing. Okay, there's a single instability band for the sine-Gordon. For the GPE, there's this secondary instability band that's appearing, and then like a tertiary instability band if you take nu tilde to be large enough. Okay, so that's nice. We now have exponentially unstable linear modes. Okay, so the next question you might ask is, what about nonlinearity? Okay, and so for that, what I'm going to do is I'm going to take these homogeneous initial conditions where the phase is displaced from the origin, and I'm just going to paste some small fluctuations on top. And this is a 1D simulation. So in the top left, you can just see what's happening. So the field's sloshing up and down. And eventually you're going to start to see fluctuations appear on top. Okay, and those fluctuations are the exponentially growing Fourier modes that were initially in the initial conditions. And you can see them appear, and they get larger and larger and larger. And then eventually you get into strong nonlinearity. And it's not completely clear, but there's waves scattering around. The top right is just the x-axis is position, the y-axis is time. So you can see the evolution of this thing through time. And you get peaks appear. A really cool thing is the peaks appear and then they kind of disappear and a homogeneous oscillation comes back and then they reappear and you end up at late times in this state that has a bunch of localized blobs of field running back and forth into each other. In the bottom left, I'm just plotting the evolution in time of the amplitude of some Fourier modes. And so these solid lines are extracted from simulations. This is averaged over 1,000 simulations. And then the dashed lines are the theory for the linear perturbation theory prediction for the growth rate. And I've taken a mode near the bottom of the instability band, near the peak of the instability band, near the top of the instability band. So those linear growth rates all match really, really well. And then a mode outside of the band that you can see initially doesn't grow until nonlinearity becomes important, and then it starts to grow. Okay.
Jonathan, a question for this slide, probably.
Okay,
This one?
Your simulation, this is a BSC, higher three-dimensional BSC, and then you are using some confinement in the other two directions.
Oh, I will get to that. This is at the moment just a 1D periodic simulation.
So it's purely 1D. Because
yeah, I'm gonna get to that later. Okay. I will show you one where I trapped one of the directions in a little bit. Okay. Because that's a good question.
Thank you.
Yeah, that's a very good question. I will get to that. This is just simplest case you could think of. Okay. Just to show it's robust, you can take different parameters, you get very similar behavior. Okay, it's not like you have to fine-tune everything exactly. Okay. So
can you go back to the simulation a little bit?
Yeah.
Okay. So here, every point is like, it's like the sign potential that you've shown on the previous slide, right?
Yeah.
And this goes up and down, okay? And that's the source of energy, okay? You understand it, okay? And so far it looks like quantum mechanics rather than field theory. Well, not anymore, but initially it looked like quantum mechanics rather than field theory. But then at some point, well, basically these things dephase. I mean, that's the how you develop spatial, variation, right? But somehow then I expect that that this energy of everyone going up and down uniformly, right, goes into some modes which are not explicitly seen, right? So I would basically expect some damping, right? Whereas in your case, it seems like they had dephased, but locally, the amplitude of up and down is no smaller than we started off. In fact, sometimes larger.
Yeah, this is a very good question. So I think what you're seeing is that's partially a peculiarity of it being a one-dimensional sine Gordon. This is something I've been looking at. So it's not this. If you put in a single mode and you kind of put it near the peak of the Floquet band and you let it go. I might have one of these. Just a sec.
Basically, in terms of the previous slide, I would expect the ball to, to damp to the bottom, right? And the way that's possible is that, energy has gone into some other stuff, right?
Yeah. So what happens in higher dimensions, but not here, is you would expect that it's like, look, I made these blobs of stuff, and then kind of those. You will turn into a system that's sort of like the mean field is sitting at the minimum, and then there's these blobs and the blobs move around. Okay. That would be, you then transferred energy from the homogeneous mode into some other degrees of freedom. Whether that happens specifically that way or not is a bit dependent on exactly what the field theory looks like. But what is true here, and I tried to point out, is that you make these blobs and then the blobs kind of disappear and you can get a homogeneous oscillation coming back, and then the blobs can reappear and then they can disappear again. So the sine Gordon equation in 1D has these crazy solutions. Well, okay, there's many crazy solutions in the sine Gordon equation. One is there are exact periodic solutions in the sine Gordon model called breathers that are basically lumps of the field that oscillate up and down, and they live forever. But this is like a peculiarity of sine Gordon. It turns out that there's a generalization of those where there's a homogeneous field that oscillates back and forth, and then one of these blobs will appear, it will oscillate up and down basically, and there will be no mean oscillation. And then the blob will disappear and the mean oscillation will reappear.
Okay. So does this have to
So, but this is like the Sine-Gordon equation is integrable and it has all kinds of special mathematical properties. So I think this thing that you're like, well, the mean oscillation hasn't really disappeared is really like descending from this like very special fact of Sine-Gordon in 1+1.
So does this actually depend on two things? One, you already mentioned that it's integrable, but is it both that it's integrable and the fact that you have kind of put in the fluctuations only once, that you have kind of sampled the fluctuations once, and then you evolve kind of deterministically, whereas in reality there could be uncorrelated fluctuations at different times.
Okay, that's a good question. Suppose that you resampled the fluctuations at every time step. So I haven't done that exercise, so I can't tell you for sure. What I think happens if you do that exercise is when you're doing sort of the linear growth phase, I think you will still get growing modes, but the growth rate will be smaller. But that might not be true. It is possible that if you resample them in an uncorrelated way, that you won't get exponential growth. But we can get into more detail about why. I think you will still get exponential growth. It will just be at a slower rate. I think once these peaks have appeared, they're kind of classical objects. So if you keep like resampling very small noise on top of them, it's probably not going to destroy this pattern that has emerged at that point. But that's just my intuition for what will happen. I haven't actually run simulations where you're resampling the vacuum fluctuations at each time step.
Okay, thank you.
Yeah. All right. Okay, let's keep going. It's not super fine-tuned. Okay, you can also run 2D simulations. So here I've just started away from when the initial fluctuations were too small to see. And what you're going to see is eventually you'll basically have standing waves develop. And this is the linear exponential growing phase. And so they keep getting bigger and bigger and bigger and bigger and bigger. And then at some point you will hit the onset of nonlinearity, and around all these peaks here, you'll see waves come out. And that's really the onset of nonlinearity in the system. And then you have waves that are kind of propagating around and these oscillating blobs that are still here. And in this case, if I plot what the mean field is doing, it really does damp down to something that's much closer to zero than the 1D case. So that's one of the reasons why I think it's like descended from the integrability of the Sine-Gordon. Okay. All right, so that's great. Hooray, preheating works. But as Silky already brought up, real BCs are not homogeneous. They exist in a trap of some sort. Okay, and so let's remove that V. Okay, and what does that mean? Well, why did I set V to 0? It was so that I can consider a homogeneous background. Okay, when V is not 0, the background is now inhomogeneous that I have to perturb around. And so a very valid question you might ask is, does parametric resonance still work? It certainly can. If you want an example in relativistic field theory, I have a paper from at this point many years ago doing this exercise in relativistic field theory. The linear perturbation theory is much harder because you have to do Floquet theory for PDEs, not ODEs. Okay, but it can be done. Okay. All right. So I'll do a reduced case of this, where we're going to imagine that instead of having, a one-dimensional BEC, we're going to have trapped the thing in 2 dimensions very tightly, and then leave one of the dimensions to be elongated. So let's think about, in that case, you'll have an effective one-dimensional BEC, but you can also imagine effective 2-dimensional BECs where you trap one dimension and let the other one be extended. So you get various types of food BECs if you want. So you could put them in a pancake trap, put them in like a sausage-shaped trap, or you could put them in a ring or a donut. Okay. And I'll specifically be looking at what this ring case does, just because it's simpler to do numerically, not for any like other reason. The big thing that you will find is if the thing is strongly trapped, and you assume that sort of the shape of the condensate in that trapped direction is constant, then you can integrate out that spatial direction. And the effect on your GPE will be that you get a GPE in a lower dimension, except this coupling G has been changed by integrating out the trapped direction. And it changes in a very simple way in some sense, where the ratio of G in the lower dimension to the higher dimension is some integral over the shape of the transverse BC shape. Okay. So you can do that and just ask what sorts of changes in G do you get. So there's some nonlinear eigenvalue equation that you have to solve. There's two limits that are kind of easy to understand. If you take G to 0, then this is, of course, the quantum simple harmonic oscillator. And we know what the ground state of those looks like. It's a Gaussian with a width given by this LQ squared parameter. If you instead take G to be very, very large, then you can drop this Laplacian term. And this is the Thomas Fermi approximation. And then you'll get a more extended looking condensate. And so on the bottom left, I'm just showing some of these. The blue is basically the quantum simple harmonic oscillator. The purple, so when G is 0. The purple is when you take G to be large, when you're in this more Thomas Fermi approximation. And so remember, there's this parameter 1 over L perp. There was some integrals I did. Okay, you can ask what that looks like as a function of this G parameter. And you should think of this x-axis as really the ratio between the width of the ground state of the quantum simple harmonic oscillator and the healing length. Okay, and so the dashed green line is the Thomas Fermi, the dashed orange line is the simple harmonic oscillator, and you see again nice interpolation between the two. Okay, all right. So I'm now going to say, I'm just going to ask a very simple question. I've got this like complicated preheating dynamics going along in say 1D, and suppose I want to trap the thing in a ring. You might ask, well, if I have all the nonlinearity happening in the longitudinal direction, does that transport itself into actually exciting fluctuations in the transverse direction? And so you can again run the same exercise where basically I'm going to say, I'm going to solve for the trapped profile. Okay, and I'll have two condensates with the same profile. I'll then give them a relative phase and let the thing oscillate. Okay. And so in the top here, what I'm plotting is the relative, the relative number density between the two condensates. The relative phase basically does the same thing. And so you can see it oscillating up and down. Okay. And as I change G bar to go from the oscillator limit to the Thomas Fermi limit, the shape of this oscillation starts to change a bit. In the bottom, I've got what the total energy density looks like. I forgot to put a scale on here. These are like 10 to the minus 6 in the purple and green. So the total energy density in the transverse direction is really quite constant as the thing's oscillating. Okay. And you can then say, well, okay, I've got this ring trap, say, I want to integrate out the transverse direction and get an effective homogeneous degree of freedom and ask what it's doing. The evolution in that dimensionally reduced system, especially for small g, basically matches exactly if you were just doing like the dimensionally reduced simulation. Okay, so the background, at least for g bar not too big, is basically equivalent to doing this integrating out of the transverse direction. Okay, so now you can do the same thing, and you can say, all right, I'm going to start with this background profile. I'm going to split the relative phase between the two. I'll put some small fluctuations on top, and I'm going to let the thing go. Okay. And so you can do that. And what you will see here, this is plotting the relative phase between the two things. So you can see in the vertical direction, the thing is trapped. You once again get the production of standing waves in the longitudinal direction that eventually break down into the nonlinear structures. Okay. So this is preheating in a trap where it's like, okay. All right. And you can again integrate out the transverse direction to reduce this to an effective 1D system. And, it basically looks exactly the same as if you had just run a one-dimensional system. Okay. And so that is where I will stop. Okay. So summary that I hope I convinced you. We can use coupled dilute gas BECs to behave as relativistic fields, which is really interesting because you can study relativistic quantum field theory systems that are out of equilibrium without having to make a bunch of approximations, theoretically. And, in my theorist brain, it's at least possible to make a setup that will mimic end of inflation in the sense that we get self-induced parametric resonance leading to nonlinearity. And you can compare these things between the BC and the relativistic field theory system in linear theory. They match with deviations being controlled by a tunable parameter. And for these specific models, there's all sorts of really interesting nonlinear solitary waves that are there. That's not necessarily true in all systems. And, at least for some more realistic things, such as adding transverse traps and this sort of stuff, everything still goes through the same. Okay, so I will stop there.